This in presentation will be about counterintelligence, specifically FinSpy. I hope you all have heard about it at some level. There's been a number of press releases about it. Around summer, a 40 gigabyte package was made public, stolen from servers from a company, a large part of which was not encrypted, so it was a good foundation for some discussion on the contents. Based on these data and on the information that has been leaked, we could know what the software, what FinSpy is able to do. I myself was interested in the technical aspects, not the brochures, but what is behind all of it. I was interested in the communication and encryption, the kinds of interactions the app can utilize. So I was interested in the technical background. Since this is a malware written not by criminals and used not by criminals, you can use this software, but only if you are authorized. You're a government or an authorized individual, etc. So it's not your run-of-the-mill malware, but I, as a virus researcher, consider it malware. So I was interested in the technique, the technology it relies on, and I was interested in getting to know what its weaknesses may be and how these can be utilized or exploited. In this presentation, I'll only touch upon the Android version. This is two reasons. First, because this version has not yet been widely discussed, and secondly, and also this is the platform that I had useful code for. Other flavors are Windows CE based or BlackBerry based, neither of which is very popular. So it made sense to analyze the Android version. Altogether, we have found 12 flavors of this app. I'd like to highlight 2 of those. The first was of interest because it was not obfuscated. It was relatively easy to analyze. Well, it was easier to analyze, to be precise. And the last 2 are the 2 last releases. Based on the release notes, these were released in December 12/13. It's pretty fresh. It's well worth comparing the 2. If we have an unobfuscated earlier version and an obfuscated new version, our task is easier because we can start off from the old version and only need to recognize the differences between the 2. And it's obviously it makes sense to start with the easier one. How do you start analyzing an Android-based app? Well, first of all, you need to analyze the access rights. From the leaked documentation, we can see that. Well, when do you see this? When you want to install such an application? They are most frequently installed by hand, and less frequently by using some social engineering or backing it into something else. So access rights are not really that important. If you are a specialist, then obviously you just want to see what the app actually is using. If you look at it as a malware, then you can see that it wants access to SMS, call logs, battery status, free space on background storage, package installation, etc. So it wants to have all sorts of access rights. Let me quickly install this version on this device. This will probably look like it was intended in the original. As you see, it calls itself Android Services. This works on earlier Androids. You will see then later on that it's com.android.services name, which you cannot do in the new versions because this is a reserved namespace, but with the old Androids it still works. Right, we have installed it. And let's now proceed. You don't see much of it, do you? What I wanted to highlight here are the services, 6 of them altogether. The names are of interest. It includes event-based services, SMS handling, internet service, removal ad service, and WATS service. These are interesting names. We'll get back to that later on. And which is also of interest is that in the case of an Android application, it's important to know what global events it subscribes to. And you see these events on the left-hand side, quite a long list that it subscribes to. We only need to specify what we want to know, and we can ask the operating system to collect, to inform us when such an event happens, and then we can do our part of the work. In the case of Windows, this is not that easy. And the service itself will start in the same manner. As soon as one of these events starts, it will start FinSpy. And in the release notes, you see the same. You need to install and then elicit one of these events, and then it'll install itself, as we will see and do. In a malware, it's always interesting how it is configured. When it gets on the target's machine, the malware will need to know whom to connect and how and when. So some sort of initialization configuration must always be included. It's either hardwired into the app or it needs to acquire these data from the outside. In this malware, in this Android malware, this is of special interest, and the way Gamma Group solved it is even more interesting. If you unpack the APs, you will find that there is an assets folder that has a configuration a folder that has a number of files with only zeros in them. But if you take a closer look at the malware, and I'll briefly show you where this happens, then you will see that once the app starts, it looks at its folder and checks whether there are any files at all, and if there aren't, then it runs this service that does this that you see here. And what it does is that in the zip file, 2 parameters can be found: an internal file attribute and an external file attribute. One is 2 bytes, the other one is 4 bytes. This means that we have altogether 6 bytes to store something. Android doesn't care about this at all, so this is potentially a good place to store information. What happens here is that for the 200 files, you see base 64 pieces that the application collects when starting up, combining them into a big base 64 string that it will use as a configuration. This is what it looks like in source code. What happens is that when the com.android services calls the com.create event when the service starts, then it'll check whether its own folder contains any files, and if it does, then it calls makeconfig file, the makeconfig file process, which reads from its own APK this base 64 string. I didn't reverse engineer it, I just extracted it. Gratefully, the GDIC GUI could create quite a nice source code. I rebuilt it as an application, and from this point onwards, I could use the author's code to read the config file from the APK. This is a refactoring, if you like. Once we have read the base64 string and converted it back to byte stream, the next task comes, which means that we need to somehow interpret this byte stream. I'm sorry about the size of this image. This is the byte stream, byte array. If you look at it, you can see that it contains a lot of strings, a domain name, for instance, QA01 Gamma International .de. So it's looks valid, and we also have two phone numbers actually in the config file. Good signal, by all means. If we continue checking this file, we will quickly see that the first parameter is a size parameter, hex 215, which is decimal 533, which is the actual size of the file. And then we see further values following this. These means type, as we will see later. And once we have this, this is a type length value kind of information storage. This is used both for file management and network communication. This is the TLV, or type length value package. If I remember right, ICQ and AOL uses something similar, so it's pretty old. Once we have reverse engineered the application and once we can assign values to the types, then the hodgepodge that we saw before can be made somewhat more legible, and this is what it looks like. As I said, the proxy can be seen with its name, followed by ports. You can define multiple ports. We'll later see how we can do that. In this case, it is easily visible that we have 4 ports specified. It'll first start on the first port and then checks the others if it cannot use the first one. We also see a plain phone and a voice phone number. The first one serves for the application to be able to liaise with the master in texting, in text messages. For which it needs a phone number, and this is that phone number that it will use. And we also have a VoIP phone, which means that calls coming from this number will switch the phone over to monitoring mode. So once somebody calls the device through this VoIP phone number, then it'll show an image for a second and then puts up a black background and tries to hide itself. But if the phone is just left on the table, you won't see a black screen, and you can and the other person at the far end will still be able to hear what's going on around the phone. There's a TUID. We still don't know what it is, but we'll find out soon. And what we also can see based on WikiLeaks are the infection numbers, how many devices can be infected simultaneously. This is a parameter, as is one that is called remove if no proxy. It is 168, which means a week's worth of time. So if it cannot connect to the master, it will uninstall itself. Since this is not an average malware, well, an average malware wouldn't be able to connect to control. In this case, this software can only be used by entitled persons, and should it get into uncontrolled hands, it must be able to terminate itself and not escalate. This is the protection that we see there. We also have a removal at date, which means that it can be removed by a certain date. What is also of interest is this here, event-based heartbeat and an event-based heart restriction. Event-based heartbeat means the events that elicit a heartbeat from the system And as you can see, here is a list of these events, and they can be configured. So these are the events when the phone connects to the master, and otherwise the interval tells it when to connect to the server. This makes it easy to limit traffic and interactions. So there is a time window after which it will communicate, even if it hasn't received any events. What was the most difficult part was the restriction bit. It's about the channel the application can use, and I'll show you where in this option I always sent zeros, which meant that the application was lying low and didn't utter a word, it didn't want to communicate. So this restriction is used for this purpose. We can specify the channel Wi-Fi, 3G, SMS, or roaming through which it should communicate, through which it should send these heartbeats. One more interesting thing in the config is the list of modules. It actually takes all modules with it. I haven't seen any track of whether or not you can add to this list, but you can switch them on and off. Logging in calendar is off and everything else is on. You also see a WhatsApp module which finds the WhatsApp database, reads it, and sends it. So it has an application-specific implementation as well. We have looked at the intents, and these were the events that the application will react on. One was on receive SMS. Obviously, this is worth checking out. At first, I thought this is the way it is monitoring SMS messages, but no. What happens is that when the on receive intent receives a message, a text message, an SMS, it is expecting a base 64 message that it will convert to byte stream, interpret it as a little endian. It extracts an integer, it throws it away, it extracts another integer, this will be j, and this will be one of two numbers, one of these two numbers, and then it starts a new intent. And what is of interest here is that we see an abort here. So if we send a message that gets at least to this point, then we can send a message that we can use to detect whether the application is present on the device or not. We will now check this function, the on receive SMS. This is my device. I have another one as well. First I'll send a hello message, just to see that the thing is working. Perfect. And now let's send a specially crafted message. Just a sec, I've used this phone so much. I have to find my way around to this message. Right, I sent this message, this specially crafted message, and haven't received it. I'll show you the message. This hello was the last one. Here, this specially crafted message was sent, but I can't see it. Let's check out what we see here. Based on this code, we can look at what this message should look like. So this was the number that the application will just throw away. This is a valid message. This is the size. This is the type. The type corresponds to this decimal. It is one of the two possible types. And this is encoded in base 64. if we send it to a phone that is infected, it won't appear because the malware will swallow it, so to say. Now let's look at how the application communicates through the network. In the case of malware, we often want to and even need to install a server that seems to be a control server, and we can then check how the app implements communication with the master, with the control server. I set up such a monitoring myself. I set up a server and simply redirected this gamma address to that server to check what happens if the application can connect. If you look at this domain name and IP address, it'll only send a reset, so the thing will not work, but the domain name still will. It'll get it. Once the connection is established, this client app will send this package to the server, which, if you look at it, once again starts with the size, a type, and a number following it. If you convert that number, it'll be decimal this long something. This is actually the IMEI, 15 digits of my equipment, which the app will send out unencrypted in plain text, followed by some other data. It will send the IMEI once again, and this is followed by an encrypted block that you can only read if you have the decryption key. Let me start something here in the background. Right, so we see that this is a starter package. We can't do anything with the encrypted part, but the first part is pretty interesting. If once we have decrypted the application, you can also see what the encrypted thing consists of. This is not the original C or Java code. I used Python because it's much more easy. It takes an SH256, it puts the hardwired key into it, and all flavors that I investigated had this key hardwired, from the oldest to the latest version. Then from the config that I already mentioned, this is it, this 000F994A, this is converted to a hex string, creating an 8-byte string from the 4-byte integer. We actually duplicated the key, but that was not really big. This is used to calculate the digest, and this hash value will be the key of the AES, and it does something similar again, a hardwired key, 8 bytes from the config, and the first bit part is the initialization, and this means this is the encryption bit. This is the procedure used for all flavors of this malware, if you want. Looking at the server, it still needs some more time. Actually, this is what happens on the other screen. It's actually trying to break to brute force. You use brute force to get to the key, as the encrypted part is also of the type length value structure. This allows you an easy brute force attack. I did with a Python-based implementation. And as you see in this version, we may take somewhere around 5 minutes to get at the key. The encryption is not really strong because a simple brute force attack on a simple computer, you're guaranteed to scan the entire key space within less than 31 hours. will probably only take a couple of minutes. Once this is done, we have a device ID, we have an encryption key, and reverse engineering the application, we see that knowing these two types of information, we can do anything, and by anything I mean are the two types that I showed. One is a master command, the other one is an emergency config. The master command is a simple solution for the event when the TCP stack is not functional, or if they don't want to use it, then you can send basic SMS instructions for instance, the app to uninstall itself, to resend the last SMS, to retry connection through the PC, or to run a tracking that can be started and stopped. These are the master commands, and we also have here acknowledges, not really important from the point of view of hacking. If we look at our small application, this I am currently in the shell in the device shell. And this is what we can see in the application map. This is the 84C something. So the app didn't do anything, only the config is present. If I am able to send the app, okay, we are done cracking the key. It thought it would take 27 hours and actually managed to break the key in 200-something seconds. So getting back here, the application is installed but has not yet been activated. But if we can send it a good master command, any command will fire up the app that is currently lying silently on the device. All we need to know is how to send a command to that app. What does a good command look like? In my case, it has to have a device ID. The IMEI number is not that unique, it's publicly available, and the application itself sent it openly through the network, so just man in the middle or simple eavesdropping will tell you the IMEI that you can put into the command, and I can request the app to resend the SMS. We only want to actually build a valid command, whatever command. All we care about is that it be valid. I can also tell it under what phone number it should store its own events. And I have a request ID, how the app should handle this command, and this will be where the acknowledgements will be sent. Okay, I send this hopefully correct master command to the app. We once again don't see anything because we have sent a command, but what is of importance is, if we look at the files, we see 4 new files. 2 are for the app, with the SM file and the VH file. It actually uses these files to flag what to do if the app freezes or something happens. Also, if I sent it an uninstall command, it would, I think, create an H file that will let it know at a restart that it should uninstall, etc. These are the two files that are important to us. Once the app starts up, it reads everything it can and everything switched on in the license. It stores this information and stores the final hashes and only checks later on whether this hash is changed or a new event happens that needs to be logged. Then new files will be generated. We'll see that as well. So the device is now live and we were able to start it. It's good but not good enough. Let's make it one better. Let's send a command. It's much more interesting because we can actually own the device. What do we need for a command? Well, we need a phone number and an IMEI number to send it to, which we can get by eavesdropping or and in the middle. And then we can reconfigure the phone. What can we say to a phone in a config? Well, practically the same as the config file has. What host to connect to, what port to connect through, a phone number, who to communicate with. And we have an emergency phone that switches the phone into eavesdropping mode, and we also have a safe mode. So we can actually overwrite the whole config or just add to it. My script overwrites the entire script. It's a total hijack. And once again, here you see the events that elicit a heartbeat, and you also can specify the channel through which the whole thing should be executed. And finally, we have a counter that stores the number of the last valid message. The next valid message should be at least one higher. This avoids using an older message, let's say, when the phone has been switched off and then back on. So the counter actually maintains the last valid message number. If our hijack, this is an integer. If we send the largest possible integer, nobody will be able to send a higher number, which means that this will be the final config of the app. But all this only lives until the app is running. Usually, as long as we don't stop it, this message will be valid. So let's look at how the message is structured. You see content components separated by slashes. Here you see some sort of disharmony. In the previous message, we described the device ID in a plain string. Here you see the same in a hex number. I don't know why they did this, but this must then be entered in hexadecimal to create a valid config file. You as a server, you have hexadecimal port number 51 is the decimal 81, and the two phone numbers. The heartbeat interval, which is a minimum value of 1 minute. So you will see we'll need to wait a little until it connects, and we overwrite the config file, and finally we see the events that elicit a heartbeat and what channel to use. Okay, let's send this message. Well, I have sent this message. Since we are in debug mode, we can easily check back to the server to check what we have done. And if you look at it, you see that the previous config, but here you can see that the phone numbers have been injected, so I was able to overwrite the previous config file, and from now on it will try to the device will try to connect to my server.
Jó, ha el akarjuk... Elnézést, ezt egy kicsit... Na igen, ez lesz. Tehát itt van a szerver alkalmazás, milyen porton.
This is the server application, the port, the key we have cracked, the 4 bytes and the device ID. These are needed partly because to enable us to decrypt the encrypted data and then also to send the correct encrypted data. If we start the server, it will, the client will connect to it, and then we can impersonate a FinSpy server. The connection has been established. It sends the config. This was the thing that we saw encrypted first, but since we broke the brute force the key, we could read it back. I sent a good response. And I can now ask questions. My request is for the app to send back the list of files. It will only send files that are RD files, and because only these RD files are the data files. And I'm querying these from the device. This is a proof of concept. Sometimes you need to restart because the server will lose synchronization, but it will download these files from the device. And we see the files. This is the current one. Here it will try to get all the files from the device. Bigger files are sometimes slow. And communication includes a lot of sleep steps in order to not make it too aggressive and detectable. So on the client side, we need to be able to sit out all these sleep cycles. If we have the key and these scripts, then we can read this file. This was the key and this is the file. If I look at it, it's pretty easy to recognize. This is actually the saved copy of my phone book. It includes Big Box and other names like Don Corleone and etc. I try to be very creative. So this is my phone book actually. So we have received this from the device. And here are the messages from the device. These are, the first file was generated when I activated the device. It picked the phone book and saved it into this file. And here you see that I received a T-Mobile text message for something. Then also you see other text message that I received. And this means also that at the end, all it does is that it gets the file list and the server says, okay, I have already downloaded them, I don't need more. So here is another command we send to the app. As you can see, it arrives pretty slowly due to the sleep cycle, as I mentioned, that make it harder for the user to connect a malware with the things that he or she sees on the device. But anyway, here is the file list. We received 3 files. We try this last one. So we will see an additional file. So you have seen that we have been able to actually recreate this connection establishment, we were able to get unauthorized access to data stored on the phone. And if I initiate a call now to this device, to this phone, it will be even slower on the screen. So it actually put up a black desktop, almost as if nothing had happened on the phone. But on the phone, I can listen to what is happening on the phone. Actually, around the phone. Actually, I'm listening to myself at this second. I managed this with the config file, and to get that config file, I don't even need to break the encoding key. If the IMEI number is known, and it is often on the backside of the device, then I can actually own it and eavesdrop on what is being talked about around the phone, around the target. This is the server and the download. The last known, in parentheses, version, this is the one we know is 4.51, which is a bit different from the previous ones. Network communication has been solved in another method. This is an obfuscated version, and I haven't spent much time on this. But one thing is clear, that the hardwired keys are the same. The communication basics or basis is the same. They probably put something random, whatever, at the beginning of the communication, and they also use an additional key, so they probably improved network communication in this new version, but this only applies to the network part. The config files, hijacking part is unchanged. These master commands and master configs have stayed unchanged, and the software cannot really protect against it. This is the way the application works. Once you are able to create a valid message, then it will be acted upon by the app. What is interesting is that I think only the newest Androids are able to create a screenshot from the app, not even the full screen. But these guys wanted to have a screenshot, a full screenshot, so it actually the program carries an exploit in it, and if it works, then it'll root the phone, and the app will be able to issue CRT calls to read the screen image, convert it to JPEG files, and store them in the screens folder of the SD card. It also includes an additional hardwired key, these 4 bytes, that is used to protect the config. We saw at the beginning in this version that the config file is stored unencoded, and in the newer versions they are stored encoded with this key. It probably means some sort of additional protection against unmasking. So summing it up, as I said, the app always reacts to these text messages. The SMS messages can be used to configure the app and send it commands. I think it's a pretty simple and pretty good solution. The phone will probably always be able to receive text messages, so this channel is open, I, as a master, will always be able to control the device. Obviously, it's important because as soon as I lose control, my use of the software, the app will be illegal. And also the device may get out from under my control and get under somebody else's. So it is of essence for me to be able to keep the device under control. Just knowing the IMEI, I am able as a hacker to trash the phone, which I think is not good enough. It shouldn't be like this. And 4 bytes for encryption, well, it's not really rocket science to decrypt or brute force. I think better encryption should be used for these kinds of apps. If we go into such depths of the application, I have shown you some sample Java codes. These need some weeks to deal with. This is the XML codes, and they are very good for reverse engineering what the application does. The most important parts are pretty Davik based. Well, my time is up, I think. Which means that they do not lend themselves well to conversion to Java code, so they need to be handled in Davik code.